Alright, so in the previous video I took it upon myself to try to sketch this, and I had already prepared a figure for it, so there was no real reason for me to do that. But I'm going to go ahead and talk through this figure now. It's basically exactly what I was trying to show in the last video. It's basically that for some linear network or some circuit that consists of resistors and capacitors and inductors, I have a signal into that circuit. So let's say that this is my signal at some frequency that I'm going to call F1. And this circuit is going to have some particular response to that input. It will probably be an output voltage as a response to this input voltage. So this might be the input voltage to the circuit, and then on this side I'm looking at the output voltage to that circuit. Could be the current. Again, if we're talking about current gain, etc., we've figured out that there are 4 different types of transfer functions, and we talked about those. One way or another, what's on the left is the input to the circuit, what's on the right is the output. And so for this particular blue signal at a frequency of F1, I kind of see that the input, so let's just write input on this side and output on this side, the input and the output are almost exactly the same, if not identical. And so that could be the case at a frequency F1, but what about if I pass in a signal to the same exact circuit, right, this exact same circuit, but I pass it in at a new frequency, a lower frequency, F2. And so the case is now we see that at that lower frequency, I have this shadow of the old signal, right? So that we can see the new signal has a slight phase shift, right? From here to here, a little bit of a phase shift, and it also has a decrease in magnitude. So it's a little bit smaller than the original signal. And so what would happen if we put in another frequency, F3 somewhere? Well, we would see maybe an even smaller magnitude, an even bigger phase shift, okay? And so what frequency response does is, instead of doing it this way and drawing every single sinusoid out, it basically gives us a way to look at a plot, which will tell us, actually 2 plots. Let me draw both of them. Let's just draw one here and one here. That will tell me what is the magnitude of my signals and what is the phase of my signals for this particular circuit as a function of the frequency of my input, okay? So I am going to put an input. For this case, let's say that my input frequency was something out here at F1, and my magnitude is 1. And I would put a dot right here. And my phase, they were the exact same. So at F1, my phase would also be 0 degrees. There's no phase shift. So I'd put a dot right here for F1. But what happens at F2, which is at a lower frequency, right? At F2, I do have some slight decrease in the magnitude. So I might draw this a little bit lower than 1. It would be somewhere down here. And what happens at F2 to the phase? Well, I have a little bit of a negative phase shift, so it might be something like negative, I don't know, in this case, what does that look like? Looks like it might be like negative 22 degrees or something. So I would draw a point right here. And for every single frequency from DC, which is 0, all the way out to some enormous frequency like 10 gigahertz, I can place these dots and sketch a curve that gives me the behavior of the phase and of the magnitude as a function of frequency for every frequency for these circuits, right? Any frequency that I want from DC, which is 0 hertz, all the way out to some massive frequency, I can see exactly what's going to happen to the magnitude and exactly what's going to happen to the phase of my output signal at a given frequency. Okay, so that again is why frequency response is so important. It's so powerful because we're almost never interested in working at just one particular frequency. That can be the case a lot of the times in power electronics and resonant converters. We are interested in operating at a single frequency. Nonetheless, we still want to see how our circuit behaves if the frequency of our input changes slightly, Do we have room to play with our circuit? And when it comes to filters, which are one of the subjects of this module, frequency response is absolutely vital for describing the behavior of the filter, showing us what signals are going to be allowed to pass through our filter and what signals are not going to be allowed to pass through. Okay, so I'm going to go ahead and end this video right here. And in the next video, I'm going to get into how do we obtain this frequency response that I've been talking about. So I've basically shown that what the frequency response is it's these two plots, one for the magnitude and one for the phase angle as we change the frequency of our input. And so I'll go ahead and end this video here. And moving forward, we're going to be using transfer functions and kind of the things that we talked about at the beginning of this module to obtain the frequency response for the circuits that we are analyzing. Okay.